Have you ever wondered how scientists identify which proteins are present in your body? Well, one way is they break down proteins into smaller parts called peptides and analyze them using a technique called mass spectrometry. But here's the catch. Each analysis produces thousands of complex signals, like a fingerprint. Matching these signals to known peptides is like finding a needle in a haystack. Slow, expensive, and often messy. That's where our project comes in. Introducing Deep Diapasef by Team Rapid Spectra X, a deep learning-powered engine that can make peptide search more than 10 times faster.
Feature extraction algorithm development from PASEF GIA proteomics data. Ever wondered how complex proteomics data is transformed into meaningful insights? Let's dive into the world of feature extraction algorithms. First off, we start with the data structure. Using alpha TIMS, we create a TIMS-TOF PASEF data object, slicing it up neatly. Each slice corresponds to a specific isolation window and retention time, forming a 2D sparse matrix of intensity values. Got that? Now, as we aggregate retention time frames, we enhance weak signals and reduce noise, crafting a 3D composite matrix. Next step? Noise filtering. We kick out the noisy signals by removing isolated points, leaving behind true signals. Using a clever convolution strategy, we keep only the relevant data to ensure accuracy. We're talking about a true data detox here. Then, we apply Gaussian smoothing to search for real peaks. These peaks become the pillars of our analysis. With local maxima identified, we fit 2D Gaussians around them, extracting crucial peak parameters. As time rolls on, we track these peaks, ensuring we capture the apex of each signal during retention time. But wait! We can't let duplicates slip through. We deduplicate peak features to keep only the best representations. Next, isotopic clustering helps us validate real peptides by checking the MZ spacing for charge states. For instance, a charge of +1 has a spacing of 1.0034, while +2 jumps to 0.5015. If the isotopic peaks follow a Gaussian-like pattern, we consider the charge valid. This is where the magic happens. If we can't estimate a charge, no worries. We assign a default charge of +2 and keep it moving. Now let's talk MS2 fragments. We extract them using the retention time window around our precursor's apex. With redundant peaks filtered out, we keep the top 25 fragments that shine the brightest. Next up is correlation-based filtering. Only fragments that dance in sync with the precursor are chosen. Imagine all the noise drowning out real signals. This ensures that we're picking only the best of the best. Finally, we put it all together into a precursor fragment feature vector, summarizing key attributes for each peak. This includes pivotal info like MZ, mobility, apex retention time, and the top 25 fragments. Pure gold for analysis. And there you have it, a behind-the-scenes look at feature extraction from PASEF GIA proteomics data. Ready to dive into your own proteomics analysis?
Feature embedding explained. Smarter, smaller peptide vectors. To make sense of it all, we need to crunch those massive datasets into something manageable. That's where feature dimensionality reduction swoops in. Each peptide starts as this complex 57-dimensional vector. Talk about a mouthful. You've got its charge, mass, retention time, ion mobility, and key fragment peaks. But really, who wants to deal with 57 dimensions? It's a total headache. So, we trained a deep learning model, a Siamese neural network. You might have heard of it. To get to this point, we used over 500,000 human peptides. That's a lot of data. We clustered them using a method called DBS-CAN. Don't worry, it's not a dance move. From these clusters, we made thousands of quality pairs, both similar and dissimilar. This trained our network to understand what closeness means in the peptide world. So, when it comes to understanding peptides, dimensionality reduction is a true game changer.
Vector-based search system for peptides.
No more slow, tedious searches. Our composite indexing zooms in on the right matches quickly. First, we index peptide vectors in our vector database. It's precision made simple.
We've created two powerful composite indices, one for CPUs and another that makes GPUs blaze through data. Using techniques like inverted file and HNSW, we ensure you find your peptide matches effortlessly. When searching, the system quickly narrows it down to a few promising clusters. Talk about efficiency.
This whole process? It's highly scalable, letting us search against billions of peptide vectors with ease. Impressive, right?
Ready to change how you search peptide data? Join the revolution. Stay tuned for our demo.